All right, well, I'm going to go ahead and get us started with some announcements here at the beginning, and then I'll introduce our speaker today. So welcome back, everybody, to the SMU Physics Department Speaker Series. We had a bit of a hiatus there, but we're back, and we're back with our first off-campus in-person speaker, Professor Kat Barger, whom I'll introduce in a second. A couple of announcements. So while you're eating, certainly don't worry about wearing a mask, even though there's a mask. The mask mandate on campus is lifted. If you're comfortable wearing a mask, we'll still encourage you to do that. I'm going to put mine back on right after I'm done talking. For questions, we have lots of folks on Zoom. I'll be monitoring Zoom on my laptop over here. So I should see if somebody raises their hand or types something in the chat, and then I'll just relay that to you and so forth. But for the folks on Zoom, if you all in the room are asking a question, we'll have to have you talk into a microphone or something like that. So I think what we'll do is, because we learned the first time that if we use this and that at the same time, that trumps this. So this is useless. So what I'll do is I'll just try to repeat the comment from the room for the folks on Zoom, or you can repeat the comment from the room for the folks on Zoom. Okay, does that sound good? Okay, okay, great. All right, without further ado, let me go ahead and introduce our speaker today. So Professor Kat Barger is an associate professor of of astronomy at physics and astronomy. Okay, I forgot to write that down. That's the one thing all right, at Texas Christian University, or TCU. She earned her PhD at the best school in the world, the University of Wisconsin-Madison. That's where all the cool kids got their PhDs, and was a National Science Foundation postdoctoral fellow at the University of Notre Dame. She explores galaxy evolution in the local universe by tracking gas flowing in, out, and within galaxies using ground and space-based observations. Many of the astronomers in our department are familiar with that melange of things. She's leading a large Hubble Space Telescope legacy archive project to explore the galactic winds of the large Magellanic Cloud galaxy, and is looking for a graduate student and a postdoc, she said hintingly, to join her team in fall 2022 for this project.
Jedi mind trick.
Yeah. Hopefully you tried that one on the undergraduates at lunch today. We're very pleased to host her here at SMU. It's really nice to be able to bring people from outside of SMU back to campus now. And we're excited for her to speak about her work. So please join me in welcoming Professor Kat Barger to SMU.
I feel like I should just start out by saying, howdy neighbors, how's it going? So corn frogs. Okay, welcome, welcome. All right, so today what we're gonna be doing is we're gonna be looking at galaxy evolution, but we're gonna look at it from the whole entire gas perspective, gas flowing in and out of galaxies. Now, why in the world do we care about gas? Well, it's the building blocks for making stars and planets. And so if a galaxy doesn't have access to its gas reservoirs, then it won't be able to make any planets and stars. So are those important? I don't know, but we sure like being here. So that's at least something. Okay, so let's pick on our own galaxy, because we all like our home field. Of course, we like the Milky Way the most just because it's our galaxy. How is our galaxy doing? Well, it turns out that our galaxy is in a little bit of a crisis right now. Ooh. Okay. There we go. All right. So it turns out that our own galaxy is in a little bit of a crisis. And what do I mean by that? It turns out that if we look at how much gas our galaxy has in its reservoir, and we look at how fast it's making stars, there's a bit of a mismatch. We're going to tear through our gas reserves that we have in only on the order of a few billion years. Now I know what you're thinking, Dr. Kat, a few billion years, that's forever. But remember, our galaxy has been around for like 13 billion years. So a couple billion years is a bit of a snap, then it's gone. So this is the predictions that we would have for our galaxy if our galaxy was isolated and it wasn't playing with its environment. And so one question we can ask ourselves is, what does the environment that surrounds our galaxy look like? Are there opportunities that our galaxy can have to fill up its gas reserves a bit? Now, we're going to look at two examples today. We're going to look at this gas cloud called high velocity complex A. It's just a relatively large gas cloud in the sky that's heading towards our galaxy. This particular gas cloud is interesting because it would represent brand new material that would be coming to our galaxy for the first time. Sometimes you get gas that is thrown out of a galaxy and then it'll get tossed up and then it can cycle back down and then it'll cause like mixing and so forth. Versus this particular gas cloud looks like it doesn't belong to the Milky Way, like it didn't come from it. And so this would be an opportunity for our galaxy to capture new gas to sustain itself. Similarly, we'll also look at some gas that's associated with the Magellanic Cloud galaxies as well. And one of the things that our galaxy is great at is that since our galaxy is so massive, it's a bit of a bully and it likes to pick on its neighbors. And in doing so, it can steal some of the material from the other galaxies or to swallow the galaxy's whole. And then in that case, it'll have more stars because it just, now has the stars of the other galaxy. And it also has the gas that comes with it. So we'll start by looking at this high velocity cloud complex. Why the heck is it called that? I don't know. Astronomers have the darndest name for things. So we have this gas cloud headed towards our galaxy. It has enough material to make about 2 million suns. Now, that's not necessarily meaning that it can make 2 million stars, because the stars it would preferentially make probably a whole bunch of low mass stars. So it would probably make a whole bunch more than 200 million stars. But if we want to make identical suns, then it could make 2 million of them. And of course, countless planets to go with them, because that doesn't take up very much of the mass. Now, this particular gas cloud is essentially on a collision course. It's heading this way. And as it's traveling towards the Milky Way, it has to travel through the Milky Way's defensive galactic halo. So this defensive galactic halo acts as a bit of a deterrent for gas as it goes through. And so what we're going to do is we're going to look to see what's happening to this gas cloud, and we're going to look at it in gory detail. What we did was we used the Green Bank telescope. It's a telescope that has a diameter that's 100 meters. So that's literally bigger than the Statue of Liberty. If this thing is huge, I got to climb up it twice. And so if you're scared of heights, because it's all like, there's a lot of holes and mesh and stuff, so you can see down really easily. It's a lot of fun. It's a lot of fun. Good times. So we use this telescope over here to observe this gas cloud, and we took over 100,000 observations. And the reason why we did that is because I don't really do imaging so much. I do all spectroscopy. And so this image here that we created, it was composed of the actual data set, was reconstructed pixel by pixel using Spectra. And since we have Spectra, we can also look at things like the motions of the gas as well. And so we'll talk a bit about that. Now, I will be a little bit honest that this particular image has been stylized just a little bit because it was for a press release. So it looks all kind of cool and flary and whatever. That's a little bit of paint job on there, but it's actual data that's been paint chopped a little bit. Okay, so this gas cloud, it's heading towards our galaxy. So this is the front part. Here's the trailing stuff, and you can see little fragments coming off. I know stylized and so forth. But the reason what is going on, and we're going to talk about some of those things and some of the morphological structures that we can see along this gas cloud. But part of what's going on is that as this gas cloud is traveling through the galactic halo contains million-degree Kelvin gas. It's very diffuse. But the thing is that when the gas cloud travels through it, an apparent headwind is created. It's the same phenomena that occurs out when it's a nice, bright, sunny day outside and you get on your bicycle. There's not a cloud in the sky. There's no wind. You get on your bicycle and then you start pedaling. Well, then what happens is your face has the audacity to slam into the air particles in front of it. And those particles start to rush past your face and past your ears and your hair, and you hear howling and stuff, but you stop pedaling. And then all of a sudden the wind stops. And so you're creating this wind because you're pushing yourself through and you're causing those collisions and you're causing that air to rush past your face. But the thing is that when you're on your bicycle, your hair blows in the breeze and all those other things. But because of the molecular bond of your hair doesn't just fly off your face. But the thing is that this gas cloud, as it's traveling through, as it's pushing through the halo, it doesn't have that same kind of molecular bond. So it can start to fragment and fly off and it can tear itself apart. And so this headwind can be pretty detrimental to this gas cloud. And so we're going to look and talk about that a little bit. Okay, so that's one phenomenon. All right, another phenomenon is that this gas cloud is headed towards a galaxy. Well, what is a galaxy made out of? Well, we have stars, gas, some dark matter, some fun stuff like that. but those stars are shining light. Some of that light that the star is shining is pretty energetic, and we know that because, you know, we get nice sunburns, things like that. But for the particles, remember, most of the gas cloud is hydrogen. Most of all the gas clouds is hydrogen, right? And so if you get gas, if you get photons that are energetic enough, then you can start to heat up these gas clouds on their way to the galaxy. If they're high enough energy, then you can start to ionize that gas cloud and heat it up. And so what we're looking at here is we're looking at a distribution map of the ionizing hydrogen photons that are emanating out of the Milky Way. Where here what we have is a representation of the Milky Way, if you were to think of it as being edge on, so not face on, so edge on here. And then what we have is the disk of the Milky Way is actually only this tiny little area here. And then above the disk, below the disk, and then through the disk. Now, if you were a photon and you were trying to escape out of a galaxy, would it be easier to go through the entire disk to get to the other side? Or would it be easier to just go straight up or straight down? Obviously, there's less crud in your way if you just go straight up or straight down. And so you get this weird peanutty kind of shape where there's a whole bunch of ionizing light that can escape above and below the disk right over here. But plus, the closest galaxy to us is not Andromeda. Our galaxy has a whole bunch of small, little tiny galaxies around it. Here are some of the larger small ones that we'll talk about later, the Magellanic Clouds. And they're also producing a radiation field. And so our gas cloud, as it's traveling towards the disk, not only is it experiencing that headwind, it's also getting bombarded by ionizing light as well. Okay, and that also heats it up. And if it heats it up, if that gas cloud dissipates and disperses in the halo before it reaches the disk of our galaxy, then that means there'll be less material that'll reach the location where stars are actually made. And so we're looking at this disruptive process. How well is this gas going to travel and actually reach to the disk of the galaxy? If it doesn't reach the disk, then it's kind of not very useful for making stars and planets. That's what we're looking at here. All right, so let's take a look at this. Look at this gas cloud. Okay, so this is the non-mucked up, photoshopped version of the map. So it's pretty good because we have 100,000 observations over here. We're looking at a surface density map of the neutral hydrogen is what we're looking at here. So this is all the neutral hydrogen. We also have maps of the ionized hydrogen. The spatial resolution is much lower because of telescopes, capabilities, sensitivities, all those other things like that. Okay, so to orientate ourselves, we have the Milky Way's gravitational pull is going down this way. Okay, so gravity is pointing down in this particular image over here. And then remember that the direction of our motion is we're heading this direction. So this is all the leading stuff, and this is all the trailing stuff. Okay. Okay. All right, so leading, trailing. Okay. Now, what I want to do before we look at some of the spectra and see what they look like, I want to also orientate ourselves morphologically with some of those weird kind of structures that we're seeing. This particular gas cloud, it's getting mangled. It's getting mangled. And we see a lot of weird hydrodynamic instabilities. It's becoming elongated and it's becoming fragmented. And that could be due to thermodynamic instabilities. It could also be related to weird kind of shocks going along the length of it. A couple other kind of fun ones is that we have that ram pressure stripping, which is the fancy way of saying that a headwind's hitting it and parts of the gas is getting pushed backwards. Okay, so ram pressure stripping is just stuff is getting pushed backwards. That's all it is. Okay, but some of it can rub off, right? Because the bonds aren't like your hair and chunks can fly off. And so we have parts of this where we have just these little fingers that are just getting pushed backwards. Can they slightly push backwards? There's a weird loopy thing right here. The loop's kind of curling over there. And so we have some signature saying that the material is getting affected by that headwind. Okay, so that's what that is. Yes?
How long is this cloud in, say, kiloparsecs or something like that?
It's probably about 10 kiloparsecs. So that's about 30,000 light years, just to translate that, because I know there's some non-astronomers in the room.
So that's about the same as the distance from where we are to the Milky Way center kind of stars.
Approximate. That's actually a good thing. Yeah, that's about a good gauge. Good. Excellent. I like it. I'm going to steal that idea. Yeah. Yes, we can. All right, so there's a couple other kind of fun morphological signatures. Now, the thing about this gas cloud is that it's much cooler than the gas that surrounds it. The halo gas that surrounds it is 1,000,000 degrees Kelvin. This gas cloud is much cooler at 10,000 degrees. This gas is much higher density. So what you have is you have a high density gas that's resting on top of a low density gas medium in a gravitational field. Well, what the heck is going to happen? You're going to start to get that higher density gas starting to drip and ooze through that lower density medium. And so you're just essentially going to get drips. And so high density material oozing through low density stuff. And so you get these like weird drippy things. Okay, so these little drippy things, globulars or Rayleigh-Taylor fingers. So this is what Rayleigh-Taylor instabilities are. And so when people are saying like Rayleigh-Taylor instabilities, all they mean is that you have something that's dripping through a lower density surface in a gravitational field. That's all that means. And we can see that here. You can see that here. Now, we have another weird phenomenon. This one's a little bit harder to explain, but let's look at what's happening on the top of this gas cloud. Notice that in addition to these drips on the bottom, we also have some weird kind of like protruding structures from the top. So that's also another interesting instability process. What's happening on that one is that you get this one's what we call a shear instability. It occurs when you have surfaces that are rubbing against each other. And what happens when you have these surfaces that are rubbing, every once in a while, you kind of get bumped a small perturbation in the tangential direction. So parallel rubbing, you can get a perturbation in the tangent direction. And then the thing is that if the material pushes down, what happens is if you run into something, that something pushes back. Okay, so then what happens is that the particles that are getting pushed down are like, I don't think so, and they push back. And then the stuff that's above are like, I don't think so, and they push back. And then you can create these weird oscillating kind of effects, and they can cause small, tiny tangential perturbations to slowly grow and grow and grow if the conditions are right. And then you can get these like weird protruding structures that come out. And so the reason why I'm pointing to the top and not at the bottom, because that could also happen at the bottom too. You know, that can also happen at the bottom too. But on the bottom, you're going to have both the drips and those shear instabilities both working together. And that's a tangled mess. You know, I can't sort out what the heck is going on with what, but I can tell that some of those are definitely oozing drips. So I can see that. Now on the top, gravity is not pointing up. And so on the top, you're not going to have those drips. So the top isn't dripping. Okay. So that has to be some of the shear instabilities or some other kind of phenomena that could be occurring. So that would be related to the top instabilities. Okay. So let's look at what the data set actually looks like. So this is a map that was created with over 100,000 spectra. Okay. So here's a small sample of what some of those spectra look like. And I cherry picked ones along each of those kind of like dense core regions where you have a whole bunch of gas. So like this right here, we're calling a dense core. We're calling a dense core here, and so forth along this fractured structure along it as it goes. And so we have them labeled over here. And so this one right here is the leading gas, core A0, the next, A1, the next, A2, and so forth down the list. So this stuff over here is the trailing stuff. So trailing and the leading stuff. And this is an example of what the spectra look like. So on the x-axis over here, we have velocity with respect to the motion of the sun. Okay, so we have a situation where we have negative velocities is material that's moving radially towards the center of that reference frame. So that's material that's moving towards the sun. And then if it was a positive velocity, that would be material that would be moving away from the sun. Okay, and this is all Doppler shifted relative radial motions. And so this works to the same kind of phenomena where you have Doppler shifts with sound, right? So sound is also a wave. And so if you have an object that's moving towards you, then the sound, the pitch increases. And if you have an object that's moving away from you, then the sound pitch decreases. Well, because light's a wave, it behaves the same kind of way. But pitch, when it comes to light, will be shifts in color. So you'll get a higher frequency if you have an object that is shining a flashlight moving towards you. It'll cause an artificial kind of compressing of the waves relative to how you perceive it. And a artificial compressing of the light waves will mean that the light will appear a little bit bluer than it would have normally. And similarly, if you take your flashlight and then you started going backwards and you shined it, then the light will look slightly redder. Remember, of course, the light's always traveling just the speed of light, but the thing that's shining the light as it's moving. So you can use that to track the motions along your line of sight. Okay, so we're using that Doppler shift technique to get at the motions of this particular gas cloud radially with respect to the sun. And on the y-axis over here, we're essentially looking at the neutral hydrogen surface density on the sky. For astronomers in the room, that's called the column density, but just to make it friendly for everyone, the particle surface density on the sky. And then what we can do is we can look to see how much emission we have moving at different speeds, and we can characterize it. And what we did was we did Gaussian decompositions. And essentially, that's a fancy way of saying that we looked at all these shapes and we fit a bunch of Gaussians to it. Okay, and we essentially assume that there's different parts of this gas cloud that can be moving at different speeds along the same location that you're looking at on the sky. Okay, so you could have a part of the gas cloud that's moving slightly towards, and a part of the gas cloud that might be moving slightly away relative to the motion of the gas cloud, or kind of doing whatever. You're looking at me, and I have different parts of my body that are moving at different speeds. You can have a gas cloud that when you look at it at different locations, it can be doing slightly different things as you're looking through the gas cloud, okay? And so this is a way for us to characterize the motions along each location that we're looking at, and to characterize, okay, well, how much light is being shined? Well, not very much light's being shined here. So that would correspond to there's probably not that much neutral hydrogen moving at that velocity. And so we're able to do that. And then we're able to also do things like, all right, well, we can also look at not just at how many Gaussians we have, but how wide are those Gaussians? And we can say things like, okay, well, how does that relate to the internal motions of how things are going? Warmer gas, cooler gas, more turbulent gas, all kinds of fun stuff like that. Okay, so now that we have that, what I want to do is I want to shift to, since this is a very rich database that we have, over 100,000 locations, I want to re-show you the surface density map, but we're going to look at it a little bit differently. Okay, so here we have to orientate ourselves. These are just coordinates on the sky relative to our galaxy. Okay, so spatial coordinates, we're looking at that same column density map. The color shift has changed. We have a white background now. This stuff over here, we have a higher surface density. So there's more particles where there's red, where there's gray, there's not as many particles there. Since we have motions at every single location in this gas cloud, we can also look at this map, but with respect to motion. And so what I'm going to do is I'm going to take this and I'm going to rotate this image into a third dimension. Position, velocity. And that velocity would be radial with respect to the motion of the sun. Okay, so we're going to rotate everything. Go. Let's see if it works. Oh, come on. Come on. This is such a cool movie. Such a cool movie. Let's see if this works. Come on. Ah, there it goes. Okay. Little zoom delay things. All right, so we're rotating. So now our y-axis is about to become velocity. And then our x-axis will be our position plane. And then we're going to take our image and we're going to rotate it around. So position on the XY plane. On our Z plane over here, we have motion relative to the sun. If we have a more negative value, the more negative the value is, the more faster that gas is moving towards the sun. Okay, so this stuff over here on the bottom is the stuff that is leading the charge towards our galaxy. And so one thing to note is notice that over here we have that reddish colors over here. Well, where's the red colors relative to the rest? It's the stuff that's leading the charge. Okay, so you have the dense parts of the gas cloud that are able to kind of like maintain their cohesiveness and then kind of push through the halo. And all the wispy stuff on the outskirts of the skin, it's getting bombarded and it's causing that material to decelerate. Okay. And so that stuff is lagging behind relative to the motion of that gas cloud. It's still heading towards us, but it's starting to slow down. Okay. Versus the orangey part is able to punch through better. Okay. So that's punching through better. So that's what's happening. Okay. And so we have another representation over here where we can dissect this data in a few other ways. We still have the position over here. Here we still have the particle surface density on the sky of neutral hydrogen, but now we also have some additional maps over here where we can say, all right, what's the line width of all those Gaussians that we fit? How wide are those lines? When you have a wider Gaussian, what that's going to correspond to is that's going to either correspond to a hotter gas, because a hotter gas means that you're going to have more random motions, right? Warmer gas, you have more particles moving towards and away from you faster, and also side to side, up and down, all those other things. So the random motion increases. Or you could also be having things like other kind of motion, like turbulence. I can't tell you which is which, but I can tell you that there's more motion along the line of sight when the line is broader. Okay, so it could be a hotter gas, could be more turbulent. And so that's going to be those reds and the purples, those colors there. And the yellow colors are going to be the parts of the gas cloud that is able to be relatively cold. And so the parts of the gas cloud that's cold, well, if we remember our thermodynamics, PV equals NKT, well, there's going to be a relationship between how warm the gas is and the density of the gas. And so, that's the number of the particles in the volume, you can relate those two. And so there'll be a tendency that when the gas cloud is colder, it's going to be more dense. Okay, so these are the regions over here. These cooler regions are regions where you tend to have, it's tricky because you can look at the shapes here and look at the shapes here, and sometimes you kind of get some matches, sometimes you kind of don't. The problem is that there's so many sight lines and there's a whole bunch of motions going along each sight line. So that makes it a little bit hard to compare these exactly directly. We'll have a couple other images where we can zoom in that'll help us out a little bit. But you can look for nice, fun correlations with what's happening with the density, the surface density of the cloud, and how possibly warm or cool it is. Over here, we have a velocity map where now we have colored over here on the color scale, motion with respect to the sun, where we have the gas over here that is leading the charge in blue, and we have the stuff that is a little bit slower showing in the red colors. Now, because we're not actually talking about how this gas cloud is moving towards the sun, what we actually care is how this gas cloud is moving towards the galaxies. What we actually care about, is it going to reach the galaxy or not? So in actuality, we should really translate all this into motion relative to the Milky Way, right? So that's what this is. That's what this is. And when we do that, we can see that over here, interestingly, that here, this material, this color is the material that's moving slower relative to the Milky Way. See, it's tricky because if you have a map like this, you can kind of trick yourself a little bit. You got to be very careful. And so over here, we have material that's moving slower relative to the Milky Way, and this material right here, which is still going faster. And so what this is telling me is that this stuff over here, it's starting to get close to the disk of the Milky Way. Well, galaxies are messy. That's where all the crud is. And so as it's getting closer to the Milky Way, it's just running into crap. And as it runs into stuff, that stuff is going to create a heavier headwind, or it's going to cause some like stronger collisions as it just runs into stuff. And it's going to push against it, and it's going to just, eat away at some of its forward progress. Okay. Versus this stuff over here, it's not running into the denser regions of the halo. It's not too close to the disk yet. But this stuff over here, it's actually getting relatively close to the galactic plane. Okay, so it's probably just running into stuff. Yes.
Just for reference on that.
Yes.
You say velocity relative to the Milky Way.
Yes.
To the plane or to a point in the Milky Way?
Yeah. Okay. So it's relative. I believe it's relative to the plane of the Milky Way. Yeah. Okay, good, good. All right. Okay, so here we're just doing a little bit of zoom in on a couple of the locations along the gas cloud. Here we're looking at portions of the gas cloud that is on the leading part that's leading the charge over here. So this is that leading core A0, and then we can look to see like what some of these structures look like. Here's our surface density map over here, and we can see some of those Rayleigh-Taylor structures in Kelvin-Helmholtz one. This one's a little bit odd though, because some of the motion's getting pushed away from the direction of, you would expect that ram pressure would cause this little thing to swirl around this way, but it's swirling in the wrong direction. And so, you know, this might be a Rayleigh-Taylor globular, but it also could be some kind of weird heating and turbulent kind of phenomena going on here, or it could be a globular that's getting pushed in the wrong direction just because it's running into a whole bunch of weird crap and it's getting a little bit chaotic in the front. So, you know, it's hard to say the entire picture because we don't actually know what the halo is doing at that particular location. And we don't know how much of the Milky Way's disk it's actually hitting. So, you know, that also makes things a little bit complicated. Okay, so we can zoom in on all those structures, but I think what I want to do is let's go ahead and jump ahead since we've seen maps like this, and we can see the widths at different locations. Let's go ahead and just correlate the widths with what we would think would be happening along the length of this entire gas cloud with respect to temperature. So what does that correlate to? And let's look at each of these small cores separately at first. Okay, so what I'm showing you here is I'm just showing you just a simple histogram plot where we just essentially take the line width, the full width half max of the Gaussians, and then histogram, so it's just the number of Gaussians that have that line width. So it's nothing fancy. It's nothing fancy at all. And then if we think of just normal thermal Maxwellian kind of broadening, you know, and that's it, and we realize that we're looking at hydrogen, we can translate to what kind of temperatures those line widths would correspond to. So that's all we did. And so here we have essentially line widths, and then here we have some markers over here that just say that line width would correspond to a temperature of 12,000 degrees Kelvin, 5,000 degrees Kelvin, 1,000 degree Kelvin. That's all it is. Now, there could be more than just temperature that is broadening up the line, but this is telling us that we get a parts of the gas cloud that is very hot and parts of the gas cloud that's very cold. And if we look at all of them, we just kind of go through them real quick. The trailing ones seem to go more towards the hotter area. Now that was the big wide blobby one. That'll be core A0. So we're back to the leading one, and now we're going along the length towards the trailing end, and it inches and inches and inches closer to warmer and warmer and warmer. And so then if we map it up, now the error bars are quite large here. I mean, this is a very highly uncertain thing, and I'm not going to pretend like it's not. But it looks like there's some kind of trend where we're slightly getting warmer, where we have angular offset from the leading core. So this right here would be the leading core over here. This right here is just the line width. Okay, so you have all the cores marked to help you see which one is which. And then over here, this is the temperature that it corresponds with. And so the leading side, a little bit colder, and the trailing side, a little bit hotter. That's weird. So the temperatures that would correspond to, about 9,000 degrees Kelvin and about 13,000 degrees Kelvin. So it's not huge. And remember that we got to be careful because this also could be related to some turbulence. So it could also mean instead of it being hotter, it could be the same hotness, but it could mean that there's extra turbulence happening on the trailing end, which wouldn't be too shocking either. Now, what is some of the things that can cause a leading part to be a little bit colder? Well, as it's running into the Milky Way, you're going to have a higher concentration of heavy metals. And when you have a higher heavy concentration of metals, metals have more pathways for the electrons to move around. And so there are some relatively small jumps that the electron can take to shine some relatively low energy light, and that low energy light can escape the gas cloud easier. And so if the leading material is starting to mix with some of the stuff that's associated with our galaxy, because all of the gas that we're looking at here, since it didn't come from the galaxy, it has a very low concentration of heavy elements. So that means that it can't cool very well by itself, but it might be grabbing some coolants as it's smashing into our galaxy or about to smash into our galaxy. And so that could make the leading part a little bit more effective at cooling, maybe. But at the same time, it could also just be that maybe they're the same temperature and maybe it's just more turbulent at the end. I can't tell you what's what, but that's two different ways to interpret this. Okay. All right. So the last thing is I want to just kind of highlight something kind of cool, just because this particular project, we published it a couple years ago. And I work with students of many ages and backgrounds. I work with high school students, undergraduate students, grad students. Pretty soon I'm hiring a postdoc and graduate students. So, you know, if you're interested in this kind of stuff. One high school student that I worked with was Cannon Hu, who started working in my research group as a high school student at the age of 9. And I just wanted to point out, because it was really cool that we worked together for 2 years on this project. And some of what he did, we essentially were mapping and playing with the spectra. We were mapping what this gas cloud looked like on the sky, and we were creating that 3-dimensional motion. So when I worked with him, we did a lot of that exploration, kind of just playing with our data and just getting to know it and just asking questions. And so Cannon was a big part of that. And because of that, you know, he's the third author on our paper that we published just a couple years ago. And he was also the youngest presenter at the AAS meeting, the American Astronomical meeting in 2017, was it? Yeah, 2017. So this is him presenting his work. So it was kind of fun. Yeah. He was 9 when he started, and I think he was 12 in this picture. I think he was 11 or 12. But he is now he's now grown up. I think he's 16, and he's a senior undergraduate student at TCU in our engineering program. His older brother is actually going to be graduating soon in our PhD program, in our physics program. Yeah, it's an interesting family.
Yeah, and he's really young as well.
Yes, but I think he's now 18. He's able to vote now. Yes, he voted in the last election. Oh, well, so that's the younger brother, but the older brother just turned 18. Yeah. Yeah. Okay. So just a couple of takeaways for this gas cloud, and then we'll talk about another phenomenon. A couple of takeaways is that we have this gas cloud. It's coming towards the Milky Way. It could supply gas to help sustain star formation. This is not the only gas cloud that's hanging around the Milky Way, but you can see that as it's going towards the Milky Way, it's got obstacles in its way. It's getting beat up. It's getting torn up. That means that as much gas as we see, it's not all going to make it to the disk. Some of it might linger around in the halo, and maybe some of that might have some halo gas condensations and fall back towards our galaxy. I don't know, but it's going to have to go through another step. This particular gas cloud can offer 2 million solar masses of gas. So it's not enough to sustain the Milky Way for very long, but other gas clouds, this is part of the whole entire cycle. So understanding how this works, how this cycle works, and studying a few of these gas clouds in extreme gory detail can really give us insight on how gas clouds move from point A to point B. So that's what this study is all about. Now that we've done that, we're going to look at another project where we are essentially exploring how the Milky Way can creatively steal gas from another galaxy. Yes?
So is this gas just like pure hydrogen?
Yeah. Okay. So most gas clouds in space, they're going to be about 75% hydrogen, 25% helium, and then a smidge of heavy elements. Technically, it's like around 2% heavy elements for like the sun. And this particular one has about 10% the heavy metal concentration that the sun does. So it's like 0.2%, you know, of its composition is heavy elements. Yeah. So it does have some, it doesn't have a lot. This has so little heavy elements in it that we think that this material might be, it might be this weird stuff that I'll explain. Okay, so when the universe first formed, the universe didn't have particles yet. All those things had to form. It didn't have stars, it didn't have galaxies, it didn't have any of that kind of stuff. So it formed stars, it formed galaxies, it formed particles. And as it was forming the universe, as it was forming gas clouds, not all the gas found a home in a galaxy. Not all the gas formed a star, those kind of things. There's gas clouds that were formed in the early universe that never found a galaxy home and is just still out there lingering. There's lingering crud everywhere. And that lingering crud is gravitationally drawn to the large, dense pockets of matter. And slowly with time, the stuff from the intergalactic medium, the region between galaxies, slowly funnels gravitationally down towards galaxies. And so we think that this is some of that leftover dredges of stuff from when the universe formed, and that it's coming to a galaxy for the first time. So that's what we think this stuff is from. Yeah, of course. Okay, so gas flows of our galaxy. Now, I told you that our galaxy is a bully. It likes to pick on its neighbor. Let's look at some of the neighbors. We have the nearby Magellanic Clouds. They've been enlarged in size so you can get a good look at them. Okay, so we have the large Magellanic Cloud, the small Magellanic Cloud here. They're only 1 Milky Way diameter away. For reference, Andromeda is 15 Milky Way diameters away. So these are right next door, but they're much smaller. This is 1/100th the mass of the Milky Way, 1,000th the mass of the Milky Way. Andromeda is 2.5 times the mass of the Milky Way. So Andromeda is a big galaxy. These are little tiny piddly satellite galaxies that are lurking around our galaxy. So when we look at these two galaxies, here's what they look like from, if you were to just look up from the southern hemisphere. So they're just cloudy little blobs that your eyes can't resolve very well. And if we zoom in on them over here, this is what the galaxy would look like in optical. Now, we're going to pick on the large Magellanic Cloud, and the reason why we're going to pick on that galaxy is because there's a lot of fun activity going on there. When we look at this gas cloud in H-alpha emission, it's a red color light that traces ionized hydrogen. So this is essentially a map of where the ionized hydrogen is. Okay, so that's essentially what we're looking at. We see that there's ionized hydrogen everywhere. And over here, we have some other ions that we also want to highlight. We have H-alpha over here, tracing the ionized hydrogen. We have the green emission, tracing the ionized sulfur. Oxygen, missing 2 electrons over here in yellow. At those locations are the locations where there's energetic stuff happening in the galaxy. What the heck is causing all that stuff? We have these little tiny like circular kind of bubbles here, and we have this big, huge mess right there. Well, when you have regions of high H-alpha emission, which traces the ionized hydrogen, that's going to trace the locations where there's a lot of star formation. Why is it tracing a lot of star formation regions? Well, it turns out that when you form stars, you're forming a tiny amount of big stars, and a crap ton of low mass stars. But the massive stars, they don't live for very long, and they're drama queens. They're like the SUVs of stars. They just tear right through their fuel, and then they die in big, huge bangs. They explode everywhere and spew their guts everywhere. And so they're violent. So when they're alive, they're shining super high energy light. Then they die and they explode and they make a mess. So these locations where there's a lot of ionized hydrogen is probably where there's a lot of stars exploding. So a lot of massive stars exploding. When you got a lot of explosions, you kick material up, down, left, right, side to side. You'll kick material through the disk of the galaxy. You also kick material out above and below the disk of the galaxy. And so in this particular case, you could generate what is called a galactic wind, where you're essentially just throwing star guts out of the galaxy. Okay, if you get enough of these explosions to happen, you can cause a big, huge wind of gas. Now, what we did was we studied this wind using this technique called absorption-line spectroscopy. And essentially what that is instead of looking at light that is being shined from an object, we're looking at light that is missing from an object. Now, I know that sounds a little complicated and weird. Basically, what you do is you get a background flashlight, and the background flashlight could be anything. It could be a star, it could be a background galaxy, doesn't matter. You want a background flashlight that is bright and it's boring. Okay, bright in whatever color you're looking at. And then what you do is you point your telescope towards that background flashlight, that flashlight over here, the light comes from here, it comes from here, and it's coming, it's going, it's coming. You have all the colors that you had when it first left the object, but then it runs into some crud. When it runs into some crud, some colors of light will get absorbed by whatever the heck kinds of particles is making up the crud that it is running into. You know, depending on how the electrons are moving around, and there's certain quantized levels and so forth. So what happens is that when you collect the light with a telescope, if we were to create a gauge where this line being flat across everything will be 100% of the light from the background flashlight, instead what you get is some divots. And those divots are related with electrons that are doing transitions that are getting excited as that background flashlight hit it. Okay, and so then what we can do is, instead of looking at that flashlight to learn about the light itself, we can look at the light that's missing, and we can use that to learn about what the heck that light is running into before it reached us. And so we use this technique. So absorption line spectroscopy, missing light. Okay, so what we did was we pointed towards a large Magellanic Cloud. We pointed our telescope, we pointed our space-based telescopes, Hubble, and Fuse is another one, far ultraviolet explorer, space telescope, I don't know, something like that. And we pointed our telescopes over there, and at all these locations with these circles, the background flashlights that we chose were stars in the disk of the galaxy. So that meant that our background target was that, and we were sensitive to anything that's between the star and the telescope, okay? And then so if there's any absorption features that would exist, the absorption would be caused by a step between the star and the telescope. And what we did was we looked at all those locations, and we quantized how much absorption we were getting based off of how big we were drawing the circle. And I should point out that this is work that my collaborators did before I joined the team. So Nicola Lenner and Chris Hauk did back in 2002 and 2007. And they pointed Fuse in this particular example, and possibly Hubble too. And they found evidence of a whole bunch of absorption with motions that is consistent with material moving away from the galaxy. Later on, we did a follow-up study where we pointed Hubble towards the galaxy, but we did an interesting little trick in that instead of just using a star in the disk of the large Magellanic Cloud, the problem with using stars is you can't see what's happening on the backside of the galaxy. And if you have a wind of gas that's being produced by supernova explosions, then you should have wind on both sides of the galaxy. And so we pointed Hubble again at a star, but also at a bright background galaxy so we could get a peek on the backside. And we did that, and we found that, yes, it does look like here's our eyeball towards the star, here's our eyeball towards the disk, towards the background galaxy. You can see the backside over here. And it looks like that when we look, we found towards a star, we only had blue shifted material, color blue over here towards the star, relative motion with respect to the sun, particle surface density again. There was material being flung at us. When we look towards the AGN, towards the background galaxy, we also had evidence of that blue shifted material getting flung at us, but we also had some red shifted material that was moving in the opposite direction from us. And so in this scenario, we then have material moving towards us and material moving away from us. And so we were able to confirm that a galactic wind does exist on this galaxy. Since then, we've mapped out the entire structure of the Nearside Wind, and we find that there's gas everywhere. So what we think is happening is we think that as these explosions are occurring, we think that because the explosions are happening in small localized regions, but everywhere we look, there's this wind. Everywhere we look, there's this wind. And so how in the world do you create a wind everywhere? So we think that the material gets kicked out, and then once it's kicked out, it thermalizes and spreads out. So what the heck does that mean? Well, when it's leaving the galaxy, it's in a high pressure zone. But then once it leaves the galaxy, it's now in a low pressure zone, so it can just spread out. And so then it can just loom. And so then you get this gas cloud that can just loom across the entire face of that galaxy. Okay. So my graduate student mapped what this wind looks like. And this is a map of the ionized hydrogen, tracing it. This is all of the wind. If we were to look towards the galaxy, where the black contours are showing you the outline of the Large Magellanic Cloud galaxy, and the darker the red is, the orangey color, that's where most of the ionized gas is concentrated. And here we have the largest concentration in this extremely active star forming location in the Large Magellanic Cloud. It's referred to as 30 Doradus. And we can go through and we can separate this into different motion, which parts are moving faster, which parts are moving slower. This is the part of the wind that's moving the slowest. And this is the part of the wind that's moving the fastest over here. And the fastest part always lingers over there around 30 Doradus. Okay, so that's super, super active star forming. Now, this particular galaxy, we're running out of time here. So I do want to point out, though, that this particular galaxy is only one galaxy. We want to take our results and we want to compare them with other galaxies. And when we do that, what we have on our y-axis right here is we have essentially a ratio of how much gas is being lost out of a galactic wind compared to how quickly the galaxy is making stars. So is it using up its gas by tossing it out, or is it using up its gas by making stars? And so the more gas, the higher this ratio is, that means it's flinging out more gas relative to how quickly it's making stars, which is not a very sustainable situation. It's like you're just removing all your gas. It's not a good thing for the galaxy. And so here, higher the ratio, more material getting flung out. Over here, we have stellar mass. This is the low mass galaxies. This is the high mass galaxies. Over here would be like the Milky Way. Here is the Large Magellanic Cloud over here. It's above these trend lines. It's above these trend lines just a little bit. So the Large Magellanic Cloud is kicking out gas more efficiently than other galaxies. But because the Large Magellanic Cloud is close by, we can observe it in exquisite, gory detail, and we can use extremely sensitive telescopes. So that this dot is above this trend line might actually be a sensitivity thing, where we just might have really good sensitive data, whereas other people can't get nearly as sensitive data because their galaxies are just farther away. So, we could be a little bit biased towards the location that we're looking at. So I wanted to just point out that we're continuing this work by looking at this wind in a huge Hubble Legacy Archive project that we have coming up over here, where we're going to begin a project where instead of looking at a couple locations using that absorption-line spectroscopy technique with Hubble, we're going to be looking at 140 different locations in the Large Magellanic Cloud to study this wind in gory detail. And so that's what we're going to be doing soon. At all of these locations, we're going to be using Hubble. And on top of that, we're teaming up with folks that can do hydrodynamic simulations. Here's an example of some hydrodynamic simulations that they made. Here's what the telescope observations look like. Some of the telescope observations already exist. We can take pretend mock observations of the simulations and kind of try to piece together an idea of what's going on there, right? Because with observing, you only get that surface density approach. You can't actually see the depth. You can't actually make out all the phases of what's happening and all the motions and all the stuff that you're just missing. And so we're going to tie in together with simulations, run some simulations, compare them with the observations back and forth, take pretend observations, take those mock observations, process them the same way, and see if we can understand the properties of this wind. And we're doing all this because the Large Magellanic Cloud, super nearby, we could never do this study anywhere else. For other galaxies, you're lucky to get one location, let alone 140. And so this will help us to at least understand the gory details of how this process works. Now, granted, we would like to understand what other galaxies are doing, because there's other galaxies, different environments, but we don't even have one good galaxy to anchor on yet. And so this will give us that anchor to really understand how these galactic wind processes work. Once this gas is kicked out, it's near the Milky Way, who's going to grab it? Possibly our galaxy, stealing it over, make some new stars out of it. So that's what I do. Awesome. Thank you so much for your time.
All right, time for some Q&A. Let me bring up the participant window here. All right, so let's start with folks online. I see a hand from Krista. Krista, go ahead and ask your question or comments.
Hi, Kat. Thanks. That was super duper interesting. I really appreciate the detail you went into with the velocities. Regarding what you said at the end about the rate at which the Magellanic Cloud is losing its mass compared to its star formation rate, I mean, it's really intense. So does that tell us anything about kind of rewinding the film and knowing when the Magellanic Clouds must have come into the Milky Way interaction? Because it's amazing there's still so much gas there and so much star formation happening.
Oh no!
Sorry.
Krista, hold on. Technical difficulty.
Important lesson. Sorry about that.
I can still hear and see you.
Yeah.
Okay.
I made the mistake of trying to be clever and move to Kat's laptop for the main display. That was foolish because the main display is tied to your microphone and speaker. So could you repeat that part of your question again? Sorry.
Yeah, just if the Magellanic Cloud is losing gas that quickly that it will essentially quench its own star formation relatively fast, does that tell us anything about how recent the Magellanic Cloud's interaction with the Milky Way has to be in terms of it still having that much gas to turn into stars at the rates that we see?
Yeah, okay, so the Magellanic Cloud galaxies, you have the Milky Way and the Magellanic Cloud galaxies. So these two galaxies we think were formed over here somewhere farther away. And we think that this binary set, which actually might be a group, there's some contention about whether it was not just two galaxies, it might actually be a group, but they're formed over here. They're tidally interacting, and then they're coming through here, coming by the Milky Way, maybe the first time, they might be on their first pass. And so some of the reasons why we think that they might have so much gas still is because the tidal interaction causes gas to get kicked out, but it's able to fall back. It's able to fall back because it just swaps maybe between those two galaxies. Whenever they have close interactions, you might trigger a bunch of star formation because it sloshes the gas around. Some of the gas gets torn out, but it kind of yo-yos back and forth in and out of the galaxy. Now, what's interesting is that because these two galaxies, we think that they actually just had a recent past where one galaxy might have punched through the other galaxy actually, and it's causing a tremendous amount of tidal debris. There's tidal debris everywhere around the Milky Way. It's crazy. But we think that since they're now passing by the Milky Way, now that when the gas gets kicked out, because they're also right next to the Milky Way, instead of falling back, some of that gas might get swooped in Milky Way tides or ram pressure stripping through the halo and slow down and decelerated. Normally, it might just yo-yo back in, but now we get a bully on the block, which now has the opportunity to be like, I don't think so. This is my gas. I'm going to put that in my pocket. So that's probably what's happening.
Got it. Thank you.
And the risk of blowing up the sun off one more time. Let's see here. I don't see any more hands raised online. Questions from the room? Oh yeah, Sully.
What's the time scale of this gas picture there? Like if we took a picture in 10 years, would it look the same?
Oh, identical. It would look identical. I think I calculated it. Based off of my memory, I think it's on the order of 57 million years. 57 million years between when this gas cloud is where it's at to when it crashes into the disk of the Milky Way. So like tens of millions of years. Yes. Yes.
Okay.
Yes.
Speaking of a gas cloud, since the density is not uniform, is there like internal gravitational influences, or is the Milky Way gravitational pull?
Oh yeah. Yeah. So usually internal gravitational influence would be, so there's a whole bunch of different kinds of matter in the universe. There's the regular baryonic, and then there's dark matter. Galaxies tend to have a very high dark matter dominant, and then some baryons, so regular gas and so forth, and things like that, and stars as well. These gas clouds, we think that they're not, that they don't really have dark matter, that they're just the gas clouds and nothing else. And when you have just the gas clouds themselves, the amount of mass that it is, even though that this gas cloud is about 2 million solar masses of material, so quite massive, it's probably not enough to be super self-gravitationally congealy like that unless it had a dark matter assist, and it probably doesn't. Yes, yes.
Right. Or comments or questions either from online or in the room? All right, I'm going to be selfish and
Yes.
ask one then. So you mentioned at the very end computational approaches to model
Yes.
outcomes. But going back to, in fact, this complex here,
Mhm.
you talked about the sort of the physical story from statistical mechanics, gas mechanics, gravity, and so forth, about what would cause each of those sorts of features we see.
Yes.
Do you, or are there people who try to model large, I mean, these are huge,
Yes.
large complexes of gas like this, and then simulate them in Milky Way like gravitational fields to see if they droop and do all that other
Yeah,
stuff?
yeah, they do simulations on it, and then when they do the simulations, they do find that those Rayleigh-Taylor, which is that shear instability, and other way around, the Rayleigh-Taylor is a dripping one, and the Kelvin-Helmholtz is a shear one. Ugh. But they do see that both of those phenomena do help to elongate the gas cloud, and when your gas cloud's elongated, it's now exposed to rubbing against the halo more, and so it can heat it up more, and that have that bigger impact from the headwind. So the more you can get that gas cloud to elongate or drip or extend out anyways, then it's going to disrupt quicker, more surface area to rub against. And so yes, they do see it, but the problem with what they're seeing in the simulations is that there's so many knobs and resolution issues and all those other things that it's really hard to create a state-of-the-art simulation if you don't have state-of-the-art observations to anchor anything. And so this is to help to anchor those simulations, yes.
And each pixel here would be what, roughly 10 to 100 parsecs, or
Oh my
1 to
gosh.
10 parsecs, something like that?
I think it's on the order of like parsecs. Yeah, I
Okay.
think so.
Okay, because you said that's about
Yeah, about 10
parsecs
10
across.
kiloparsecs across. Oh, maybe it's like tens of parsecs per pixel. I can't
10,
remember.
yeah, okay.
I can't
But
remember
still,
in all
sort of
honesty.
That's a lot of gas.
Yes,
obviously have to simulate,
right.
Even if there's only like roughly 1 hydrogen atom per cubic meter.
Yeah, getting a simulation at this resolution would be very tricky. I mean, I think they're starting to have those capabilities, but yeah, I know.
That's
They're
impressive.
getting there.
Yeah.
They're getting there.
All right, last chance for questions either online, I don't see any hands raised, or in the room. Okay, well, if not, let's thank Professor Barger one last time, and we'll close out the event. Thank you.